In number 22, we're to graph the function and tell whether or not it has a point of discontinuity at x equals 0, and then if there is one, to tell whether it is removable or non-removable. Now, I'm going to take you a little further than the directions here, but just because I think it's what's best for you in terms of your big picture understanding. And before you start this video, you might want to pause it and look back at page 3 of your study guide to review the discontinuity types and how they show up in the graph. The first thing I want you to do with this picture in your packet that I've included is to write in, on, around the graph, but not in the vertex of this parabola, and you'll see why in a moment. But underneath the graph probably be the best place to write it. Write in bold print, this graph is a liar. And put that in all caps. Now that's really important because that's kind of the point of this particular example. Now, the reason that we know this graph is a liar is that when we look at this function with a little more sophisticated eye, what we see is an x in the denominator. And we also see that in the top we have an x we can factor out. And that, whether or not that x factors out, determines what kind of discontinuity we're dealing with here. So when I factor x out of the top, I have x squared plus 1 as my second factor, and I have an x in the denominator. I would like for you to also develop the habit that when you see what's about to happen here, and that is that these two x's cancel, that your slash you're used to making for things that cancel, you turn it into an arrow and write whole, because that's where a whole comes from. And then once that factor cancels off, whatever's left, which in this case is x squared plus 1, is what your calculator will graph. Because your calculator does not have the capability of graphing a hole in your graph to show you that there's actually a hole there. So we know that there is a discontinuity there. So what I would like to see on your paper after you've done this work and written whole is that there is a removable, let me see if I can write here, a removable discontinuity at x equals 0. And the only removable type is a hole. So now let's come back to our picture and update it by hand to show what's actually going on here. And that is that at 0 for this graph, there is a hole. And I can't seem to draw one very well here. Let me see if I can make it a little bigger. And then I'm going to color in the inside to emphasize, oops, let me undo that. I'm going to color in the inside to emphasize that it's actually a hole there. So here we have what the graph should actually look like. Now the size of that point is exaggerated, but there is a missing spot in this graph because of that canceling x. And if you don't know that, you'll misinterpret a lot of graphs. So you have to be smarter than your graph, or smarter than your graphing calculator when you look at your graph. Now let's look at number 24, same set of directions. And this graph does not appear to have any kind of discontinuity, but again, after that last one, you should be on your guard and be prepared to do analysis if you need to. The good news here is that this graph is telling you the truth. There is no discontinuity, and we can verify that because the only discontinuity g of x is going to have is where the denominator equals 0, so we know that x can't be 2, which shows up in the graph as a vertical asymptote. So there's the discontinuity, which is accounted for, but the question specified that we're interested in what's happening at x equals 0, and at x equals 0 we have a defined point, which we can confirm analytically by plugging 0 into our function, which would give us 0 over 0 minus 2, which is 0 over negative 2, which is 0. So if my input is 0 and my output is 0, that means that the point 0, 0 is on the function. So with these directions, what we would say is that there is no discontinuity at x equals 0. Then we move on to number 26, which tells us to state whether each labeled point identifies a local min, a local max, or neither, and identify the intervals on which the function is increasing or decreasing. So we need to look at what's happening at 1, 2, 3, 3, and 5, 7. So let's go ahead and list those points, and we'll record our analysis as we go. So we're going to go in order. So 1, 2, and then we'll have the point 3, 3, and then the point 5, 7. And then remember that a minimum or a local minimum occurs where the graph goes from decreasing to increasing at that point. And it doesn't have to be for a big interval, it just means in some little neighborhood around that point it is the lowest point there. So if you think about tracing this function coming from the left, we are decreasing until we get to 1, 2, and then when we leave 1, 2, we're increasing. So that makes 1, 2 a local min. And then for 3, 3, as we move towards it, we are increasing, and then as we move past it, we're still increasing, which means that 3, 3 is neither. So that would be neither. And if you think about it, at 1, 2, 2 is the lowest point that it hits because of the fact that to the left of it is higher and to the right of it is higher. At 3, 3, on the left it's lower than 3, and on the right it's higher than 3. So that also, from that perspective, gives us the same information. So then we continue our little traveling along this function, and as we leave 3, 3 and head towards 5, 7, the whole time between those 2 points we are increasing, and then when we leave 5, 7 we are decreasing all the way to the end. But for that purpose it doesn't really matter. It's decreasing to the right. So increasing to the left, decreasing to the right makes 5, 7 a local max, which is what your eyes kind of tell you by the fact that it's a high point in that little vicinity. And so then we want to talk about our increasing, decreasing intervals, and this function starts out decreasing, so we'll list that first. So this function is decreasing on negative infinity to 1, based on this picture, and then it increases after that, so we'll list that possibility there below it, increasing on the interval from 1, 2, so it's increasing from 1, and it keeps increasing until you get to 5, so that would be from on the interval, the closed interval 1 to 5. And then after that, on the right of 5, so we're going to come back and say, and bracket 5 to infinity. And that's how you describe your increasing, decreasing intervals. Then on number 30, it says to graph the function, identify intervals on which it's increasing, decreasing, or constant. So we don't have to talk about maxes and mins. We're just talking increasing, decreasing, constant. So again, the best way to think about this from an intuitive perspective is that as you trace the graph from left to right, the graph falls continually until it gets to this little point right here at the corner, which is at -1. And we describe our increasing, decreasing intervals because that's a characteristic of the path that you want to tell the interval on which it's happening, which is your x-coordinates. So that would be decreasing on negative infinity to -1. And then once I get to -1, as I travel along the graph, I'm going in a horizontal path. In other words, I'm neither going up or down, so that would be constant. Anytime you're traveling in a horizontal path, that's constant. So this would be constant on -1 to +1. And then to finish our little trip across this function, we leave 1 and we climb and we climb and we climb right out the edge of the graph So then that means that the function is increasing on 1 to infinity. And that's all you need for 30. And that's the end of the video.